So the ratio and the ratio test in particular is one of my personal favorites, and I like to use it whenever I can. It's very, very useful, and when we get a little bit later down the road and we start talking about the radius of convergence, right, you have to perform the ratio test in order to test for that most of the time. So let's look at what this test does. So the ratio test tests for absolute convergence. So if it's testing for absolute convergence, then if you're a bet man, you'd probably want to bet I'm probably going to take the absolute value of some stuff, right? Because that's how we test for absolute convergence. So if we let the sum of a sub n be a series with non-zero terms, the following two things will hold. The series converges absolutely if the limit as n goes to infinity of a to the n plus 1 over a sub n, like so we take the absolute value, if that's less than 1. So once again, right, nerds are lame at naming things, ratio means fraction. So you literally create a ratio of the terms. And then to test for absolute convergence, you take the absolute value. And then you'd look at the limit. So what we're saying here, if you're getting the limit of a fraction is less than 1, right? We're saying that the denominator is getting to infinity faster than the numerator. That's what a number like less than 1, that's what a fraction less than 1 is, right? The denominator is bigger than the numerator. So these terms are reducing, right? And if they're reducing at a rate where it comes out to be less than 1, then we know that series is going to converge, because we're simply just taking a number that's less than 1, less than 1, less than 1, less than 1. We're reducing it over time. If the root test, right, so the series will diverge if the limit of the ratio is bigger than 1. So now the rate of growth is bigger in the numerator than the denominator. So if you get a number larger than 1, it's clearly going to diverge. So this test is actually very useful because you can test for convergence and divergence and you get an answer when you're done. That's also what I love about the limit comparison test. If you perform it correctly, you're done because you know whether it converges, you know whether it diverges. Right? Also for divergence, if the limit of the ratio is infinity, it diverges. So any real number greater than 1 or infinity means divergence. But what number did we not include? 1. So if you perform the ratio and you get 1, the test is inconclusive. So if you come out that the test is inconclusive, that means you got to perform another test. So what this result's telling you is we can't tell a difference between the first term and the next term as it's going to infinity, that they are so close together that they're basically 1. So you need to perform another test. So you can't assume divergence here. You can only assume divergence if it's clearly greater than 1 or infinity. If it's less than 1, it converges. If it equals 1, you got to do something else. Okay? So this test is really good for series, oops, that rapidly decrease. Okay, so the ones that go to 0 very fast. Right? So you're going to look for series involving exponentials and factorials. So pretty much any series where you've got a factorial, this one's your guy. Because you can't really do a lot of algebra with factorials, you can't really take the limit, but if you stack a factorial over a factorial, we can easily cancel things, right? Same thing with exponentials. If you stack an exponential on top of an exponential, we have a lot of algebra tools where we can separate things and cancel stuff out. So when you set up these ratios, and we're going to do some examples, you're going to set up the ratio, you're going to simplify the ratio, and then take the limit. So what I would do is set up the ratio first, don't start jumping right into the limit, simplify everything, and then just take the limit of the result. So let's see what we mean. So if I have 2 to the n over n factorial, we know the limit of the nth term in this case is going to be 0 because factorials dominate exponentials, but we still have to do a test to confirm convergence. So let's set up our ratio. So we say we're going to take the absolute value of the nth plus 1 term and put it over the nth term. So in this particular case, the only thing I really need the absolute value for is it would wipe out any negative terms. I don't have anything negative in this, so I automatically know the absolute value is just going to return the original function, so I can just drop the absolute value bars, right? So the nth plus 1 term is 2 to the n plus 1 over n plus 1 factorial, and when I divide by a sub n, right, we multiply times the reciprocal. So I'm going to get this. Two to the n plus 1 is 2 to the n times 2. So that means the 2 to the n in the denominator is going to cancel the n out of the numerator. The 2 to the 1 is still there, okay? In factorial, right, says multiply 1 through n. This says multiply 1 through n plus 1. So the first n terms are going to cancel, so it just cancels the factorial sign, and all you're left with is 2 over n plus 1. Yep.
Okay, so how did you cancel out 2 to the n and 2 to the n?
So 2 to the n plus 1 is 2 to the n times 2 to the 1. Yeah. And then, does everybody remember the factorial math we did, right? So if n is 5, right, you've got 1, 2, 3, 4, 5 in the numerator, but you have 1, 2, 3, 4, 5, 6 in the denominator, so the first 1 through 5 cancel, so you're just left with the last term, right? So this is what we want to take the limit of. So if we take the limit as n goes to infinity of 2 over n plus 1, we get 0, which is less than 1. So it passes the test, and the series converges. More importantly, it converges absolutely because we took the absolute value. So if I alternated this series, I know it would also converge. I have fun with these. These are just puzzles to me. And so much goes away. I like it when stuff reduces down. All right, so if I want to set up my ratio, I'm going to get n plus 1 squared times 2. And when I plug in n plus 1 here, I'm going to get n plus 2. And the same thing's going to happen in the denominator. I'm going to get 3 to the n plus 2. Then when I multiply times the reciprocal, right, I have this. So the squared stuff isn't going to cancel, right? But when I set up my fraction, I want to group that together. So I'm just going to say, remember, if you have something squared over something squared, I can write that as n plus 1 over n quantity squared. I'm allowed to just combine it into one fraction. All right? So now what do we do about these 3's and 2's? So 3 to the n plus 1 is 3 to the n times 3, right? 3 to the n plus 2 is 3 to the n times 3 squared. So right off the bat, we know that the 3 to the n's are going to cancel. And similarly, the same thing will happen with the 2's. So the 3 to the 1 in the numerator will cancel out with one of the 3's in the denominator. So this guy will go away, and I'll just end up with 3 to the 1. Same thing will happen here. The 2 in the denominator will cancel one of those 2's in the numerator. So all I'm left with is n plus 1 over n quantity squared times 2/3. And so if you think about what those exponents were saying, I had one extra 3 in the denominator and I had one extra 3 in the numerator. So that's why I just ended up with 2 over 3. And once you play around with these and you get used to these exponent and you practice with your exponential rules, you'll start seeing this stuff because it's a lot of repetition, okay? So this is what I want to take the limit of. So what's the limit of the stuff inside the parentheses? Just 1. So the limit of this is going to be 1 squared times 2/3, or just 2/3. 2/3 is less than 1, so our series converges absolutely. So it worked. Good. All right, so this one's a little funky because we're going to have n raised to the n power. So this is going to make the math look a little weird. But there's a factorial here, so the ratio test absolutely applies. So if we set up our ratio, I'm going to get n plus 1 raised to the n plus 1 over n plus 1 factorial. And then we're going to divide that, right? So we multiply times the reciprocal. And I'm going to get times n factorial over n to the n. So the factorials are easy to cancel. We just saw this, right? We know the n factorial in the numerator is going to cancel the factorial sign out of the denominator. But let's do one extra algebra step so we can see how to break up this n plus 1. So this is n plus 1 to the n times n plus 1 to the 1. In the denominator, I still have my n plus 1 and my n to the n. So the n plus 1 in the numerator and the n plus 1 in the denominator will cancel. And since everything I have left is raised to the n, I can write that as n plus 1 over n raised to the n. So this is what I want to take the limit of. Now, remember, you can't just say this is 1 to the n, so it's 1. That's not how this works, okay? We actually have a limit, right, where we said we had one of our known limits where we had an expression raised to the n, and I'm like, this might be a version of e, okay? So in order to tell that, I'm going to actually split the stuff up inside. So this is the same thing as saying n over n plus 1 over n. So n over n is 1 plus 1 over n, and that is in fact equal to e to the 1. So is e greater than or less than 1? Greater than. So this is greater than 1, so this thing diverges. Yep. Here to here. So if you've only got one term in the denominator, you can split, right? Because that, like, if I had n over n plus 1 over n, right, you can combine the numerator because you have the same denominator. So you can do the same thing in reverse. That's just n over n plus 1 over n. And n over n is just 1. So, but when we write it in this form, we can see that this is e to the 1, right? If I had it flipped the other way, so it was n over n plus 1, well then that would have been 1 over e, and 1 over e is less than 1, so it would have converged. So if I flip the original series upside down and put the factorial on top, this is an example of a series where you can have a factorial in the numerator and it converges because n to the n is growing faster, right? So one of the things you want to make sure, like when you're doing the root test or the ratio test, is pay attention to what types of things converge and diverge, because it'll really help you when you're studying and you're like, okay, so we know that factorials grow faster than exponentials, right? And now we know that n to the n beats a factorial, right? So it's not the biggest boy on the block anymore. Okay. So let's look at something like that. So we could try a ratio test on this, right? Because one of the things you want to do with an alternating series is test for absolute convergence, and a ratio test does that. So if we test for absolute convergence and it converges, right, we're good. So let's set up our ratio. And we're going to have the absolute value. I've got to keep the absolute value bars now because I have some negative stuff. So we have the absolute value of -1 to the n plus 1 times the square root of n plus 1 all over n plus 2 times n plus 1 over the square root of 1 to the n, or sorry, -1 to the n times the square root of n. So the absolute values are wiping out the negative terms. So now I can drop the absolute value signs and try to simplify this expression. So what I have is n plus 1 times the square root of n plus 1 over n plus 2 times the square root of n. So all I did was regroup things, so I had the square roots on one column, right, and everything else on the other. And I can take this one step further. Since the square root is just the power 1/2, these are both raised to the same power, so I can actually combine them into one fraction. So I can say, well, what I really have is n plus 1 over n plus 2 times the square root of n plus 1 over n. And that's what I want to take the limit of. So what's the limit of the guy out front? 1, right? The limit of the stuff under the radical is 1. So basically what you have here is 1 times the square root of 1, which is just 1. So if we get 1, the test was inconclusive. So nice try, but the ratio test doesn't work. And that should kind of make sense, because what you had was a linear term in the denominator and the square root in the numerator. And we said the ratio test works best when things are rapidly increasing or rapidly decreasing. These things grow to infinity, but not very fast. So the ratio test just wasn't good enough. And so what it's saying is the square root of n versus n is kind of indistinguishable when you stack them on top of each other as they get to infinity, right? So we have to try something else. Well, since it's an alternating series, we can try the alternating series test. So the a sub n term is just everything that's not the negative 1. So this stuff is positive, so it passes that. The limit, as n goes to infinity, of the square root of n over n plus 1 is going to be 0, because n to the 1 in the denominator is a higher power than n to the 1/2 in the numerator. So it will go to 0, but it will go to 0 very slowly, right? But it does get there. So then we need to check, well, are the terms decreasing? So if you try to compare the square root of n plus 1 over, sorry, n plus 2, sorry, I lost my spot, to the square root of n over n plus 1, okay? Well, that's kind of a tricky thing to do, because we've increased the numerator and we've increased the denominator, and if you try to do this algebraically the way we were doing it before, the algebra gets really messy and the inequality is just not clear, right? So we actually have another way we could very easily test if this thing is decreasing. So does anybody remember from Calc 1, how did we test if a function was decreasing or increasing? What did we look at? Second derivative was concavity, the first derivative, right? So you would take the first derivative, set it equal to 0 to find any maxes or mins, and then you would test intervals, and if the function, the derivative was positive, the function was increasing. If the derivative was negative, the function was decreasing. So square root of n over n plus 1 could be written as a well-defined function that we could easily differentiate. So this won't come up often, but you need to understand that if the inequality just isn't clear and you have to test, right? If you could write it as a function of x, you can just take the derivative, right? And check that. So if we look at the derivative of this, let's dig deep, guys, right? Quotient rule. So the derivative of the first term is 1 over 2 root x, right? And then you say times the second term minus the first term times the derivative of the second term, and the derivative of the denominator is just 1, and you put that all over the denominator squared. So this actually simplifies into 1 minus x over 2 root x times x plus 1 squared. And so all I did there was I got a common denominator in the numerator, put everything over 2 root x, simplified it, and then when I multiplied times the reciprocal, I ended up with this, okay? So one thing to remember about the function of x is when you look at the derivative, you had to plug an x value in to see what was happening. So you use the original series for that. So the original series was going from 1 to infinity, so we only care about how the function behaves when x is 1 or greater, okay? If you look at the denominator, well, the square root of x always has to be a positive value, right? X plus 1 squared will always come back as a positive value. So the denominator is always positive here, so we're good. So all we really need to test is what's going on in the numerator, right? So if I plug 1 in, that's the lowest value I'm allowed to have, well, that's 0. That doesn't really tell me much, right? But if I plug in 2, I get negative 1. If I plug in 3, I get negative 2. So if I plug in any value greater than 1 to infinity, I get a negative over a positive, which means this guy is negative for all x greater than 1. So what did we say when the first derivative was negative about the function? It's decreasing. So that's what we wanted. So if it's decreasing, this thing passes the alternating series test and it converges. And remember, we looked at earlier when we looked at sequences that if you have a sequence or a series that looks like it could be rewritten as a well-defined function of x and you plotted all the values in your sequence, they would literally just look like dots on the line of the original function. So we know that as the series goes to infinity, it's going to behave in a similar manner as the function going to infinity. Okay? So I think this is a good place to stop because the root test is next and we only have like 15 minutes left and I'd rather just start that fresh on Monday. So we'll just call it here.